All right, let's dive right in. Today, we're going on a journey, zooming way past what our eyes can see to figure out what the world around us, and yeah, even we ourselves, is really made of.
I mean, just look around you for a second. The screen you're looking at, the chair you're in, even the air you're breathing. It's all matter. And get this, from the tiniest speck of dust to the biggest star out there in the galaxy, it's all made of the exact same fundamental stuff.
So that brings us to the big question, right? It sounds almost deceptively simple, but what is matter? Well, that's one of the deepest questions you can ask in science. And it's that very question that's going to be our guide for this whole thing. Okay, so where do we even begin? Well, to really get what matter is, we got to start where the very first scientists did. And what did they do? They just looked around. They took all the stuff in the world and started putting it into categories based on, what it looked like, how it felt, and what it did.
Check out this super simple experiment. You've probably done something like this without even thinking about it. If you stick a metal spoon and a plastic spoon in some really hot water, you already know what's going to happen, right? That metal spoon handle gets hot, and it gets hot fast. The plastic one? Not so much.
And just like that, this simple little observation shows us a really key property. We'd say the metal spoon is a thermal conductor. That's just a way of saying it lets heat travel through it super easily. And the plastic spoon, that's an insulator. It basically puts up a roadblock against the flow of heat. And this isn't just a, that feels hot kind of thing. You can actually measure it with real numbers. So look at silver. It's got a thermal conductivity value of 429. That is an amazing conductor. Now look all the way down at the other end, air is at 0.024. I mean, that's a huge difference, right? And that massive gap, by the way, is exactly why a big puffy winter coat works. It's not really the feathers keeping you warm, it's all the tiny pockets of air they trap. So that's one property, how well stuff conducts heat. But matter can do something even more dramatic. It can totally change its form. And this brings us to something we all learned back in grade school: solids, liquids, and gases. Water is the perfect example, isn't it? We see this every single day. When it's a solid, we call it ice. You add some energy, heat it up, and it melts into liquid water. If you keep adding energy, it boils and turns into the gas we call steam. And of course, if you take that energy away, the whole thing just goes backwards. But here it is again, that big question. Why? Why does adding heat make solid ice turn into liquid water? What's actually happening on a level that we just can't see? To figure that out, we have to zoom in. I mean, way in. All right, let's do it. Let's zoom in and see the real story. It turns out that everything we've talked about, how well something conducts heat, why things melt or freeze, it's all because of this constant, invisible dance of tiny little particles that make up, everything. Okay, so here it is. This is the big reveal. On the left, that's our world: solid ice, liquid water, and steam. But on the right, that's what's really happening. See? In a solid, those little particles are packed together in a tight, orderly grid, just kind of vibrating. In a liquid, they've got more energy, so they can jumble up and slide past each other. And in a gas, they have so much energy, they're just flying all over the place, totally free. Now, scientists have a name for this whole idea, of course. They call it the kinetic molecular theory. But the main point is actually really simple. It's just this: everything is made of tiny particles, and those particles are always moving. The more energy they have, the faster and crazier they move. And that's what makes something a solid, a liquid, or a gas. This table here just sums it all up perfectly. If the particles have low energy, they're stuck together, vibrating, that's a solid. Give them some more energy, and those forces holding them get weaker. Now they can flow. That's a liquid. And if you pump in a ton of energy, they just completely break free from each other and zip all over the place. That's a gas. It really is that straightforward. Okay, so this leads us to the next big question, doesn't it? What are these little dancing particles? Answering that question, it takes us to maybe one of the single most important discoveries ever: the atom. The actual fundamental building block of everything. But here's the thing. We didn't just wake up one day and know what an atom looked like. It wasn't a single aha moment. As you can see from this timeline, it started as just an idea, a philosophical concept, way back in ancient Greece. And then it took like 2,000 years of scientists doing experiment after experiment, each one building on the last, to get to the picture we have today.
So, for a while, after a guy named J.J. Thomson discovered this tiny negative particle called the electron, this was the best guess for what an atom looked like. People called it the plum pudding model. The idea was that the atom was just this big blob of positive stuff, with these little negative electrons scattered around inside it, kind of like raisins in a pudding.
But then, everything changed. Another scientist, Ernest Rutherford, did this landmark experiment with gold foil. And what he found just blew the plum pudding model out of the water. He discovered that all the positive stuff, and pretty much all the weight of the atom, was packed into an incredibly tiny point right in the middle. He called it the nucleus. So goodbye plum pudding, hello to this new planetary model. And just to give you a sense of how mind-bogglingly small that nucleus is, this analogy is perfect. Imagine an atom is the size of a huge soccer stadium. The nucleus? It would be a single pea sitting on the center spot. Just think about that for a second. The implication is just staggering. It means atoms, and so everything, including you, are almost completely empty space.
Okay, so we've got a nucleus in the middle and electrons flying around it. But guess what? We can zoom in one last time. Let's crack open that tiny little nucleus and meet the three particles that are the real, final blueprint for literally everything in the universe.
First up, inside that nucleus, we have the proton. It's got a positive charge, and honestly, it's the most important one for figuring out what you're dealing with. The number of protons is what defines an element. If an atom has 1 proton, it's hydrogen, period. If it has 6, it's carbon. That number is like the atom's permanent, unchangeable ID card.
Hanging out with the protons and the nucleus is the neutron. And just like its name sounds, it's neutral, no charge at all. It basically does two things. It adds some weight, and it acts like a kind of buffer, or nuclear glue, that keeps all those positive protons from repelling each other and flying apart.
And last but not least, we've got the one zipping around on the outside, the electron. It's super tiny, has a negative charge, and here's the cool part. In a normal stable atom, you have the exact same number of electrons as you do protons, so that positive charge in the middle and the negative charge on the outside cancel each other out perfectly, making the whole atom neutral.
So there you have it. This is it, the master blueprint for everything. And just look at the table for a second. The mass difference is wild. The proton and neutron are the heavy guys, and the electron is almost 2,000 times lighter. It's barely there in comparison. And the charge? It's just so simple and elegant. +1, 0, -1. That's it. That's the entire toolkit. And that leaves us with this one final, truly mind-blowing thought. If every single thing, I'm talking you, the planet, the sun, everything, is built from just these 3 little particles, then what makes something like gold different from the oxygen you're breathing? What's the difference between a chunk of lead and a diamond? It's nothing. Nothing but the number and the arrangement of those exact same 3 building blocks. It's an entire universe of unbelievable complexity, all built from just a handful of incredibly simple rules.